Computer. Okay, recording has started.
Okay.
Sorry, go on.
Yeah. So, hello everyone, and welcome to a new seminar in this our seminar series, Cage Gravity by the Gods. Our speaker today is Jishnu Goswami, who is currently an AIC, who is a postdoc at RIKEN AICS Center in Kobe. So Jishnu did his PhD from IIT Kanpur. He completed his PhD in 2017. After that, he was a postdoc at Bielefeld University for a few years, during which time he joined the Hot QCD collaboration. And now, I mean, since 2022, he has been at RIKEN in Kobe in Japan. So he's here to tell us about his recent work, which is about searching for the QCD critical endpoint from lattice QCD. So a word about the seminar. This is a new seminar series which we've started a couple of months ago, and the idea is to bring speakers from gauge theories and lattice gauge theories and gravity together on a common platform. Provide a means for them to interact and collaborate with one another. We've had four or five talks so far, and this will be the first talk in this new year. So we will mute. I mean, the seminar is for an hour, and we will be muting the audience. So if you have a question, post it in the chat box, and one of the moderators will relay the question to Jishnu. So with that, let's all welcome Jishnu, and over to you.
Okay, so how long can I speak then?
1 hour, 1 hour. We started at 4:05 now, right? It's past 4:05. So you have an hour. It can be up till 5:05.
Okay, thank you. So I will talk about searching for the QCD critical point. So let's start with the QCD phase diagram first. So the QCD critical point is a conjectured critical point which happens at some non-zero values of baryon chemical potential. So this conjecture phase diagram, x-axis is the baryon chemical potential and y-axis is temperature. So what we know is that at this our current understanding from theoretical calculation, that at this zero chemical potential at lower temperature, the strong interacting matter stays in a hadron gas, and at very high temperature, so this is about 155 MeV, it turns to some quark-gluon plasma, and then at very high temperature, it becomes a free Fermi gas. What one conjectured is that when one goes to a high chemical potential, so currently this change of the phase from hadron gas to quark-gluon plasma is known to be a smooth crossover, not a true phase transition. And it is conjecture from model calculation that this crossover will turn to a first order phase transition. And of course, then there will be a first order phase transition will end in a second order phase transition or a critical point. So this is the QCD critical point or critical endpoint that I am and also we are searching. And in experimentally, one understood that there are two experiments currently going on. One is the RIK at non-zero chemical potential, and one is ALICE that's operate here at zero chemical potential. So in experiment, how they change the chemical potential is that they change the so this is a heavy ion collision experiment. So when you change the beam energy, collision beam energy, then it's eventually changed. That means that changing the baryon chemical potential. However, still, so this is actually, so the question is that, is there any signature for a critical point? So that question is both yes and no. So I will go through all the findings and from the experiment and theoretical. And so one thing is that, so we know from our thermodynamic knowledge that certain thermodynamic observable will vanish close to a critical point For example, order parameter or skewness or kurtosis, or sorry, order parameter will not diverge, but susceptibility, skewness or kurtosis, this will show some divergence close to this critical point. So we had two tasks. One is that relate our theoretical lattice QCD calculation with experiment. So this experiment, these are known as the conserved charges, which are baryon number, electric charge, and strangeness number. The cumulants like susceptibility, skewness, kurtosis of these numbers are expected to diverge close to a critical point. So one can relate theoretical calculation with this experimental observation and try to find this signature of the critical point. And in this talk, however, we will talk about more.
Hi, Jishnu. Sachin has a question. What is skewness?
So skewness kurtosis is how, so if you have a distribution, then this is the fourth order cumulant is the kurtosis, or ratio of fourth by second order square. So is the Binder cumulant is the kurtosis. So is that okay?
Yeah, that's fine. That's fine.
So basically Binder cumulant is the kurtosis, and then skewness is the third derivative, and so we will also come to that point. But yeah, so now okay, and also using the cumulants, one can construct equation of state like pressure and energy density, entropy density. So in this talk, or number density, so in this talk we will focus on calculating the pressure using these cumulants, and then we will try to find different methods to indirectly way to find this critical point.
Sachin has one more question. You can see it in the chat.
Yes, is there also a useful third order Binder cumulant? So third order is the skewness. So that so Binder cumulant of course will not diverge, but Binder cumulant will have some universal value. So I guess skewness will diverge, go to 0 maybe.
Yeah,
so
thank you.
for,
Thank you.
yeah. So this is the current status on the critical endpoint search from the experimental, and is there any more question?
No. I will, yeah.
Okay, sure, thanks. So the question that, sorry, not question. So this is the current update on the critical endpoint search from the experimental point of view. So this is the like R42 baryon number. So this is basically the similar to kurtosis. Sorry, I don't put the definition, but so this is similar to kurtosis of baryon number, and this is the comparison with experiment are the kurtosis of the proton number. And so as we discussed that close to a critical point, the higher order cumulants are expected to diverge. So that's why one could see a non-monotonic behavior at high baryon chemical potential or low beam energy. Sorry, this is I forgot to mention. So one also observed that high baryon chemical potential means actually going to smaller and smaller beam energy. So this is this probably so this is actually the star collaboration said that this could be a hint for a critical point that one saw a non-monotonic behavior in this kurtosis of proton number. Uh, However, from the equation of state, QCD equation of state calculation, we don't see or we don't find a hint for a QCD critical point on this whole beam energy range. So in this talk, I will actually discuss in detail how we arrive this conclusion, or how we get this conclusion that we don't see a critical point in this whole beam energy range from the equation of state. So let's now go through. So this talk will be based on these two papers, one from this hot QCD collaboration, this paper, where in the first part of my talk, I will discuss Taylor expansion and Padé approximation of pressure at finite chemical potential. And there is also this paper. In the second part of my talk, I will focus on multi-point Padé approximation of number density. This is done simulation at non-zero imaginary chemical potential. So, so is there other question? Okay, no. So these are also the other works that is done and currently going on. These are some of the list of references, and yeah, so I'm sorry that I did not. So Prasad also have a lot of work here which I have not included. Sorry, but so these are more or less some of the references I included. So let's give you a first hint that, or sorry, introduction. So this is the partition function of the QCD, where we have this mu is the quark mass and mu u is the quark chemical. Sorry.
No, that was just an echo. That was just an echo. Go on, go on.
Okay. So this is the quark mass and quark chemical potential. So those who are not familiar with lattice QCD calculation is that so it's basically we discretize the Dirac operator of quarks on a space-time lattice and then perform the calculation on large-scale supercomputers. However, like if we naively discretize the Dirac operator, then that causes some problems. So there are a lot of prescription one has to use to avoid those problems. So one of these discretization prescription known as HISC, which is the abbreviation, it means highly improved staggered quark. And 2+1 flavor means that we use two degenerate flavors, where our light and two light flavors has the same mass, and we use heavier strange flavor. So this 1/4 factor come as we use this particular discretization scheme. And there is one more problem is that when we introduces this real chemical potential, we cannot perform these calculations in a supercomputer numerically, because we don't have an algorithm. So unless in future maybe AI or quantum computing can solve that. So unless that happens, so currently what we do is that there are two methods. Either one could simulate this with the imaginary chemical potential and then perform analytic continuation to the real chemical potential, or in this talk, as we do, that we expand this in a Taylor series. And as you see that our QCD partition function has written in terms of the quarkical potential. So this is the relation which one can use to convert this quark chemical potential to this baryon electric charge and strangeness chemical potential. So basically quarks to hadrons. And so these are the accumulants at vanishing chemical potential. So for example, these are related to susceptibility and skewness and kurtosis. So of course that will also depend of the observable that we are talking about. But okay, so we will come to that point also later. But here, so this is the derivative that I was talking about, that second order means susceptibility, third order relate to skewness, and fourth order derivative with relate to kurtosis at vanishing chemical potential. And similarly, if one takes derivative of this quantity, then similar way one also can construct this susceptibility, skewness, and kurtosis at non-vanishing chemical potential. So so this is basically the pressure of the QCD in terms of this baryon electric charge and strangeness chemical potential Taylor expansion. So now, as we discuss this, so how we calculate this the expansion coefficient is that we need to take derivative of this det m. This m is the Dirac matrix that I previously introduced, and this will then eventually convert that. We need to calculate the stresses of these large sparse matrices. So it's not possible to evaluate the traces exactly. So we need to use stochastic trace estimation, which is basically we introduce a right-hand side, like a Gaussian random noise or Z2 noise, and then calculate the traces using stochastic trace estimation. So basically we need to use a lot of in principle, one needs to use like a very large number of sources to get this correct trace. Otherwise, there will be a large stochastic noise. But in practice, of course, we need to see that the computing resources that we have or computing power we have to satisfy ourselves with a limited number of random numbers. And so one realizes that when we go to higher order derivatives, then this number of terms will get more and more, and so that become noisy. And so when one wants to calculate higher order expansion coefficient, then one needs to have like a huge number of statistics. So this is as we did, I told you that I show you. So far, like for example, last 10 or 12 years, hot QCD able to calculate only 4 expansion coefficient, the second order, fourth order, sixth order, and eighth order. Although eighth order comes with very large errors, as we discussed that this requires a very large gauge configuration or high statistics. For example, with our data currently, we can able to, so these are 4 lattice spacing for this, and these are 3 lattice spacing for the fourth order. So this is not very important. So what important in this discussion is that using this 4 expansion coefficient, we can construct up to 8th order in Taylor series, and then we have to understand the radius of convergence or the reliability of the Taylor series of the pressure. And so one thing one could notice is that this stays positive for all the temperature range, and this changes sign around 140 or something. And okay, this also has very large error, but this also become negative in this range 135 to 165. So the radius of convergence of the Taylor series as a function of temperature or the reliability of the Taylor series will depend on these 2 expansion coefficient. Okay. So as I said that this is the pressure series, and this is the number density, which one obtained by taking 1 mu v derivative of the pressure series. So this is the expansion coefficient of the number density, and this is the expansion coefficient of the pressure. So just to differentiate these two, that the reliability of the Taylor series is depend on that the good agreement between subsequent orders. And then of course there is also question of that this number density, as I said, that this obtain one derivative. So of course one sees that the factorial which suppress the higher order coefficient, because our higher order expansion coefficient have larger errors. So this is suppressed with a larger factorial than this. Then of course the reliability of Taylor expansion will be smaller for the number density than the pressure series. So one can also define the estimator for the radius of convergence. And since we derive this from a single Taylor series, then all the estimator that we actually use when we take k tends to infinity limit, this would give us the same radius of convergence. So this is what I just said. So for example, for the pressure, one can define estimator for the radius of convergence like this is the usual ratio estimator, and for the number density this is the ratio estimator. And so we see that when one takes this k tends to infinity limit, they become identical. So what I just said is that can be concluded like that reliability of the Taylor series can be improved by including more higher orders as long as we are inside the radius of convergence. But if we go beyond this radius of convergence, then of course this will not work. So we will also come what is mean by the radius of convergence, or what controls the radius of convergence of a Taylor series, right? So this is actually for that I took a test case for this is used like Fermi gas, a massive Fermi gas. All these M, E are actually dimensionless. So this is M by T, mu by T. So one can exactly calculate this pressure in Mathematica. So this will look like this black solid band. And of course, we know that this series have singularities, which will be m plus minus I pi, which is the closest singularity. So this will actually control the radius of convergence of this Taylor series, this singularity. And this singularity one can guess is m square, not guess, calculate m square plus pi square, which is, sorry, this will be equal to, this is 3.18 for this parameter value, 0.5. So here, as you see, that this is the second order Taylor series, and so lower order, actually lower order series like fourth order or eighth order are probably a good approximation for the exact series. However, when we go to higher and higher order, we saw that the Taylor series does not converges to the original curve, but rather it started to diverging. And when we include more higher and higher order terms, we will saw that this actually started to diverging close to its radius of convergence. So basically, if there is a pole in the complex axis or real axis, this will indeed control the radius of convergence of a Taylor series. And so however, what we can do is that we can construct a Padé-approximant. So a simple Padé-approximant, what in Mathematica one can just give the function and give the variable and give at what one point one wants to use this Padé-approximant. And as you see that although the second order is this 2 Padé is not so very good approximation of the original Taylor series. But when we go to higher order Padé-approximant, this slowly converges to the original function. So basically, if there is a singularity in the complex plane, this will affect the convergence of the Taylor series if we include higher and higher order. But this will not affect the convergence or of a Padé-approximant. So in that sense, we want to use this Padé-approximant for our pressure Taylor series of the pressure. And of course, also Padé-approximant, we can look at the pole of the Padé and analyze its behavior. So again, this is another just example of this Fermi gas that one can for finite n, one can define an estimator of the radius of convergence like this way. So this is the usual ratio estimator, and this is the Mercer and Roberts estimator. So here I try to plot this, and as you see that, of course, when we go to very high number of terms, then these two should be same, which is this here. But we saw that when we go to like here, the convergence is very slow when the number of terms is finite. But while the the ratio estimator is converging slowly or poorly, while the Mercer-Roberts actually indeed are much more stable and maybe a better can show a better convergence. So, but as I said that we only have up to 8th order of Taylor series. So, so what we can do at most is using those 8th order 4 expansion coefficient and up to 8th order Taylor series. So now to searching for this critical endpoint using Padé approximation. So what we know from model calculation is that the QCD critical point will exist at a lower temperature than the chiral transition point. So the chiral transition happens when the light quark masses are 0, so which is estimated around 130 MeV. And so this is kind of like what we expect. And from Li-Yang theorem, we know that the phase transitions are related to singularities of the Taylor series on the real axis. So if we find the singularities at complex plane, then we know that they are not single signature for a QCD critical point. So so instead of as I said that instead of examining, so we only have 4 expansion coefficient up to 8th order. So that may be better that we construct Padé approximate, which is the rational function like this, and then calculate the singularities of this function, and then maybe try to relate that to phase transitions. So now we have this pressure series, and as I discussed that P2 and P4 are strictly positive for all temperature. So what one could do is that rescale it like that way, and then one sees that really the at least for 4 up to 8th order in Taylor expansion, we can construct 4-4 diagonal. So we can construct this type of combination. But in this talk, I will mainly focus on this 4,4 diagonal Padé approximate, and the poles of this diagonal Padé approximate will be controlled by these two expansion coefficient. So so this is what we learn from Fermi gas example. The convergence of Padé approximates will be unaffected by a singularity in the complex plane, while also for the Taylor series, this will control the radius of convergence of Taylor series. And and the closest singularity will also be the radius of convergence of the Taylor series. So and what we find from 4x4 Padé is that this is quite interesting. That pole of the 4,4 Padé, when we get so due to the symmetry, when we get two pair of complex poles, we saw that this is indeed similar to this Mercer-Roberts estimator. So from using this, so as I said, that the occurrence of a complex pole or real pole will only depend on these two expansion coefficient for the QCD case. So here we try to we construct this 4,4 Padé like this way. So this is the general structure, and so and from here we try to find that what value of this sorry let me just sorry what value of this C82 and C62 actually in this parameter range will give us complex pole and will give us real pole. So from this we saw that this yellow line this will give us this pair of complex poles, and here this will be like two imaginary imaginary real imaginary and real. So so for our case we will, as we said, that we expect that critical point will be below 130 MeV. So in this range we expect that the poles will be complex in this temperature range.
Jishnu, sorry, I had a question. So what is being plotted here exactly?
This C82 and C62. Sorry.
And yeah.
So this C62 and C82 is basically related to chi6 and chi8. So we rescale this in a such a way.
Uh-huh. And then what do the colors? I mean, like, what does the color mean?
Right. So this is the color means that, so we can then write a general structure of the 4,4 Padé like this way. And then we solve for this denominator like this way, z plus minus. And then we can define solve this and try to find a parameter range where the poles will be complex. So here CC means complex. And here this II means the pole will be imaginary. And IR means imaginary real, and real imaginary, and real.
Understood. Okay. But I mean, for the physical significance, the poles ought to be real, right? So
Right.
only the RR is important, really, is it?
Right. So if it has to relate to critical point, yes.
So that's what, one is eventually interested in, kind of.
So this is the general structure. So here we don't use any values or any simulations. So this is just from analytic structure.
Right.
So this is
But
just
the same thing when we plot using the lattice data, I guess we will be most interested in RR region, is it?
right. So we need to see if our falls in this region or not. So so as I said here that we know that the CEP will exist at a lower temperature than 130 MeV.
Yes.
So in that sense, we will expect that. So first thing that we need to prove that we see only complex poles in this
Temperature range. Yeah. Thank you. Yeah.
So yeah, thanks for the question. So this is now the QCD data. So this is the triangle that if our data falls inside. So as Prasad, as you see that this lower temperature data actually has a tendency to go out to this RR plane. So we probably in future need more statistics to actually see if this stays inside this triangle and go outside. Go outside, then that could be our signature for a critical point.
Sure. Understood. Yeah. Thanks.
So as we discussed that,
But just last thing. So these errors are after 1.5 million configurations. So it's a difficult, challenging thing, is it?
million, yes.
Yeah. Okay. Yeah. Thanks. Thank you. Yeah. Oh, go on, please. Yeah.
Okay, thanks. So as we discussed that if our this QCD data falls inside this triangle, then of course the poles will be complex. So which we saw in this temperature range, and so as this green data at low temperature could be a signature for a critical point if it falls in this go outside of this triangle. And then we saw that if it is falls in this RR region, like this region, and this is the actual poles of the real part and imaginary part, and this also tells the same story that we go to smaller and smaller temperature. Then we saw that this indeed show a signature for moving to the real axis. So then this could be so if that reaches real axis, then it could be a hint for a critical point. But provided that, then of course, if we saw that it goes to a real axis, then maybe we need to also increase the Taylor series and Padé to really see that this real axis pole is stable. Then we can actually say then this is the true signature for a critical point. So currently, what we found is that in temperature wise, the critical point has to be smaller than this 135 MeV. And so this is the radius of convergence plot. So 2 by 2 Padé actually shows us this ratio estimator, and 4 by 4 Padé it shows us this Mercer-Roberts estimator. And when we go to this lower and lower temperature, from this we so this is the lower end is around 2.5. So from that we kind of conclude that the bound for CEP has to be greater than 2.5. Right. So so far our preliminary conclusion is that singularity of the pressure series using Padé approximation of eighth order Taylor series is that there is no hint of a singularity up to 135 MeV, and the corresponding mu v by T is 2.5. So this actually says that we find no indication for a critical endpoint in almost the entire beam energy range covered by the BES2 in collider mode. So if one has to search for a critical point, then one has to go lower than this temperature and higher than this chemical potential. So this is the first part of my talk. If you have any question, that also good, or I can then move on to the next part. So in my next part, I will talk about multi-point Padé approximation. So as Prasad mentioned slightly that since we already have 1.5 million gauge configurations and higher order Taylor expansion does not seems feasible, because as you already eighth order after having 1.5 million gauge configuration, we have very large errors. So there is one alternate method one can think of, that one can perform simulation on multiple imaginary chemical potentials and then construct multi-point Padé. The advantage of that is that this is similar to the normal Padé approximation. One will have a linear system, but instead of going to very higher order in a expansion coefficient, one could actually construct a Padé approximation based on smaller orders in Taylor series. So what we do is that we simulate this multiple imaginary chemical potential. So this is the imaginary part of the number density. This is the chi2b, and this is chi3b. So then in this way, this serves actually two purposes. In future, one could also then do analytic continuation to the real values of the chemical potential. Or what one can do is that one can also inspect the singularities of the Taylor series. And so the question is that what these singularities actually means in the complex chemical potential. So this will, before going to that, I just want to mention something. Let's do a small exercise. So the universal scaling function in the vicinity of second order phase. So far we have talked about critical point. So critical point basically means that second order phase transition is happening. And so the close to a vicinity of a second order phase transition, one could write this universal scaling function. And so this is like when one taking, so when I talk about skewness and kurtosis, so this way one can also define the universal values of order parameters. So when one take derivative with respect to h, then one can define the order parameter of susceptibility, skewness, kurtosis of the order parameter. And also one could take derivative with respect to T, and in that sense one can construct energy, specific heat like observable, and also like third derivatives can relate to skewness, and fourth derivative relate to kurtosis. And so this and then one can also of course do a bit rescaling and get the values of the universal value, what they will be look like. Either they'll probably will diverge at infinite volume. And so one can also construct this like a finite size scaling function and determine this universal values. So so T is actually temperature like scaling field, and H is magnetization like scaling field H. And so what the usual practice is that one put this to 1 and then determine the value of the scaling factor B and then put it here to rescale this equation like this. So this is the infinite volume scaling function. One can also do a finite size scaling function as well. And then this Z is look like this. So to find the Lee-Yang edge singularities, what we need to solve for is like this way. So ZC and Z0C like this way. So in this way, so in this paper, it shows how one can get Lee-Yang edge singularities for different spin models like ON models or Z2 models. So now what we will do with this Lee-Yang edge singularities, right? The question is that, okay, we understand how to get Lee-Yang edge singularities. So how can we relate that to QCD, or what we will do with this Lee-Yang edge singularities? So, oh, sorry. Ah, sorry, my slides kind of messed up. So this is the so I'm extremely sorry, my slides kind of messed up. So this is what I want to talk about. So the Lee-Yang edge singularity. So as I discussed in my previous part of the talk, that we are not currently at a critical temperature. So from there, so what can we do when we are not at a critical temperature, right? So then comes this concept of Lee-Yang edge singularities. So when one is away from the critical temperature, then what one could show is that this singularities which control the radius of convergence of Taylor series or Padé-resummed also can behave like a universal way where the position or the position of the Lee-Yang singularities are universal, and the closest singularity from the expansion point um, is the Lee-Yang singularity. And this maybe we could try to find, and then we see that when we approach the critical temperature, how that Lee-Yang singularity goes to a real axis. So so where this has become a bit confusing, right? So as we discuss, this is the Lee-Yang edge singularity one could get. So in QCD, one could have a chiral phase transition when the quark mass vanishes. So the difficult part to get this Lee-Yang edge singularities are to know this variable like T and H, where so for some cases we know this scaling and scaling field, and for some cases we don't know the scaling field. So for example, for the chiral phase transition, which happens when the quark masses vanishes, for this case we know the scaling fields, which is basically H. The quark mass is the symmetry breaking field, which is magnetization like scaling field, and this T is reduced temperature. So in that way, we can then put this T and H here and chiral phase transition. However, for the critical endpoint, we don't know this T and H. So this is one of the difficult part to find the Lee-Yang edge singularities, which is related to QCD CEP. So to really test that our method that we actually wanted to talk about our work. So first we need to do this calculation or find this Lee-Yang edge singularities on a known system or known phase transition. So so first, let's discuss about this possible Lee-Yang edge singularities for the critical point. So as we know that the critical endpoint belongs to this Z2 universality class. However, we don't know this T and H. So So this is, we use a linear mapping like this way. And then there are several unknown parameters. And we put some educated guess from FRG calculations. So this is we put from FRG calculations. And this is we put from, this is calculated in lattice, this curvature of the critical line, pseudo-critical line. And this is the pseudo-critical temperature. And this is we put some ad hoc values. So this trajectories of Lee-Yang edge singularities for the QCD critical point look like this way. So here, as you see that this stays complex, and this at smaller temperature, this has a tendency to move to the real axis. This is somehow we also concluded in. And now let's first discuss this, that our method actually works, or we can get some known singularities from known phase transition. So this is the phase diagram of QCD in a imaginary chemical potential plane. So this is the temperature, and this is the imaginary chemical potential. So the mu I is actually quark chemical potential. And when we convert this to baryon chemical potential, this pi by 3 will be pi. So this actually phase transition, and since this is the imaginary chemical potential, we can directly perform lattice QCD calculations. And here actually for this lattice spacing, one does this calculation and find this TCRW is around 201.4 MeV. And so for this Roberts-Weiss phase transition, we know this small t and small h like this way. So then we can put this in this equation, and we can find the value of the real part and imaginary part of the Lee-Yang edge singularity. And so this is kind of a testing of our method, that can we find the Lee-Yang edge singularity, or is the closest singularity identified with the Lee-Yang edge singularity. So okay, this is already a talk about. So there are three critical points in QCD. One is this Roberts-Weiss critical point, which will happen at this TRW, and when the it is at pi, and one is the chiral critical point, which will happen at this 0 quark mass. So this is we don't know. So this is our unknown. So we will first try to show that our method works on this known critical point. And this actually we will not discuss here. This is our future work. And we will also try to get some results for this QCD critical point, which is the most interesting one. Right. So this is the Lee-Yang edge singularities for the Roberts-Weiss phase transition. So as we discussed that for second order phase transition, this will work like this way. And the Lee-Yang edge singularities, we can get that this imaginary part will be pi, and this real part will be like this way. So we see an appropriate scaling of the Lee-Yang edge singularities for the Roberts-Weiss phase transition, that when we go approaching this Roberts-Weiss temperature, then we saw that the singularities are moving to the moving to the Roberts-Weiss transition point. And we have used three methods to construct our multi-point Padé. One is this, we solve a linear system in the mu-b plane. And then we also do this general chi-square method. And then we try to construct a Padé in the fugacity plane, and then mapping back to mu-b plane. So basically what the conclusion is that at least for the Roberts-Weiss singularity, when we do this scaling, we saw that this is indeed consistent with the expected Lee-Yang edge singularities. So in that way, at least our method works to determine this Roberts-Weiss phase transition. And so now this green one, this will be the trajectory for the Lee-Yang edge singularities for the chiral phase transition. and this red one will be the Lee-Yang singularities for the critical endpoint. So as why this has to go to the real axis to become a true phase transition, right? Or like to identify that as a QCD critical point. So this way, so again I come back to the same thing or same question, that how we identify the QCD critical point, because we don't know the value of this T and H. So according to this Stefanov, we can use linear mapping and then write this Lee-Yang singularity by solving this equation. So just remember that these are all unknown parameters. So what we can do is that we can try some fitting, or one could use some fancy way. So I will discuss what I did or we did here in this case. And as I discussed that to become it is critical point, the imaginary part has to vanish and it has to reach the real value of the chemical potential. So what we try is that machine learning model for the Lee-Yang edge singularities. So this is like a very preliminary first try. What we did is that we described this called MADE, mass autoencoder, for density estimation. So what we did is that we basically generated a lot of these singularities using Gaussian bootstrap method, and then use this real and imaginary part for training, and then we determine the probability of the real part and imaginary part as a function of temperature. So this is a very fancy way of fitting this as a function of temperature. But one advantage, or maybe one future use this can be, is that this can be extended to any other parameters, like for example quark mass or volume or lattice spacing. So this will also help us for a better interpolation of the real and imaginary part, because as we discussed that all of the parameters are unknown, so one needs to feed that to get those unknown non-universal parameter. So this is the poles that we get from our multi-point Padé. We have currently this 4 temperature, and this is a comparison with the 4x4 Padé. This also shows a tendency to moving towards the real axis, and this also probably we guess that this could be poles related to QCD critical point. Um, this also so we are I mean this is we understand, because we think that this slope is a bit steep, and this shows also a tendency to move towards critical point. But we need to do more work to understand that the differentiate between the chiral Lee-Yang singularity or this is related to critical endpoint. So currently, as this seems the slope is seems more steeper, than we thought that this may be um, uh, could be like related to critical endpoint. So this is also one can find the similarity between the 4-4 Padé poles and the poles of the multi-point Padé. So by knowing this singularity, real part and imaginary part, now we can use our machine learning model to interpolate this between temperature. And so currently, as I said, that currently we only do this as a function of temperature. We get the distribution of probability distribution of this real part and imaginary part. So in future, we can also include to get a larger parameter space, like include quark mass and also volume. So anyhow, so this is like our first try to do this critical endpoint extrapolation. So this is the 4x4 Padé that we get earlier, and this is from our multi-point Padé. So this we use this machine learning, and we use a function like this way. Sorry, there will be a square. I'm sorry. Because this is a parabola, so this has to be a square, right? So this, as I said, that we need to extrapolate this. So the one disadvantage of machine learning is that we cannot extrapolate. Um, um, we cannot extrapolate beyond our data, observed data. So then we need to use this machine learning model and this unknown function to extrapolate to this point. And we saw that when this goes to 0, the value of the critical endpoint is around 630 or 590 or something. So this value is not very important. The important value is, of course, the temperature, so which is around 100 MeV. But this is like on a particular lattice spacing 6 and 8. And so this value are kind of consistent with FRG calculation or Dyson-Swinger calculations. Right. So this is my summary. So we have developed a multi-point Padé method to extract positions of singularities from number densities in the complex mu plane. And so this can be seen as this Taylor expansion method and analytical continuation. And so we test our method with this well-known Roberts-wise transitions. And then we try to use some ansatz to extrapolate this Lee-Yang singularities for the QCD critical calculation of and trying to find for the chi. Yeah, thank you.
Thanks for the nice talk. We'll take. Does anyone have questions?
Yes.
Maybe. So that is for real, or is it the actual critical endpoint?
Critical endpoint.
New simulations, right? Or is it
Imaginary mu find the singularities also in the real axis.
on the real axis?
There is a real part. We can actually try to see how that moves. So get singularities then, and then you can study the
what's your prediction? Less for the temperature.
maybe. All right. So this is actually, yeah, this may be a lot of systematic effects. The less systematic error. That the imaginary
Values.
yeah, maybe the fixed, yeah, will be the reach. Okay, there is a yeah.
Yeah, Parmeshwar. You know how Dyson-Swinger values are? Do you know what they are?
I guess if I and the chemical potential is around 600 or something FRG.
I see.
Yeah,
I
DS
ask
value
two
is
questions.
Mhm.
Shall I ask two questions?
Yeah, please.
Yeah,
The
go.
first is there any check of this kind of calculation in real-time quantum field, soluble quantum field theory model? For example, maybe in 1+1 Schwinger model, something like that, with the chemical potential.
Yeah, so
Check.
sorry, I forgot to mention that, yes, for smaller, for Goswami model, and so this actually, I'm extremely sorry, I did not add the reference. But yes, so for Goswami model and Ising model, this actually done the Lee-Yang singularity and finding the phase transitions. Yes.
No, but your method works there well.
Yes.
Okay. There is a second question. I think some time ago I heard Rajagopal from MIT claiming that at high temperatures, in coagulant plasma, instead of becoming asymptotically free, it became strongly coupled. And he said it was a very surprising result, and it is surprising. So can you comment on that result? You may know about it. I don't know much about it.
Yeah, so that is actually so are you talking about like non-equilibrium?
I don't know.
strong
I mean, I am not in this field, but we heard a seminar like that in Chennai by Rajgopal, okay, in January, I think. I think
yeah, so that is the standard nomenclature. People say that this is a strongly coupled coagulant plasma.
no. He said that as temperature is increased, the QCD at those temperatures became, instead of becoming asymptotically free, became strongly coupled.
Sorry, I don't.
Okay.
So actually, yeah. So is it from experimental data or because theoretical lattice QCD calculation, we do equilibrium thermodynamics. So in that at least we find evidence that it goes to free Fermi gas or Boltzmann limit.
He was contradicting it. Whether it was from experiment or from calculations, I don't know, but he was contradicting that statement. So
Yeah.
that is the reason I asked you. Yeah.
Okay, so thank you for letting me know that. So in our lattice QCD calculation, I always saw that this goes to Boltzmann limit.
Can we conclude, because it is an ongoing discussion, that quark confinement is not proved at all?
I think it's a little, so I think what Rajgopal was probably talking about was at high temperatures. I think what Jishnu here has been talking about is more about chemical potentials. I mean, somewhat high temperature, like 150 MeV, but mostly about high chemical potential. So it's really like two separate discussions here.
Yes. My question was, since Goswami is an expert, I wanted to have an input on that. Okay. Likewise, I wanted some input. There has been some arguments whether quark confinement is a slogan or is it somehow established. It is used, I don't know, it is used all over the place. But is it simply a slogan or is it a reality? From what you say, it is not proved. So I would like to have a confirmation. And the related Sanathan also told me the same thing. And a related question is, if quarks can become free in this phase diagram at some region, then can one check its scattering amplitudes? Free, I mean, quark, because it is asymptotically free, means there will be asymptotic states and there will be scattering. Can we measure it? or at least imagine measuring it.
So actually, I guess Prasad has this paper of calculating this QCD equation of state at very high temperature. So maybe he can make some comments.
Scattering amplitudes is real time. It's a real time calculation.
Yes.
And this Wick rotated thing in general, I mean, in general, it cannot. But there was a formula by Lucia some years ago, which related these scattering, at least two particle scattering amplitudes, to the energy levels of a system in a box. So through that formula, some scattering amplitudes can be calculated, not all of them. And recently, I think people have also extended it to cover three particle scattering amplitudes. But that's about it. In general, it's not possible. In some special cases, it's possible.
Yeah, so are you saying then that quark's confinement is not proved?
Like confinement, deconfinement, phase transition.
Is there the statement that quarks are confined, even for small temperatures, high temperature, whatever, is not proved? Okay. One talks about scattering amplitudes. It cannot be confined.
So actually, yeah, so I want to make one small comment on this, what Prasad said, that maybe in future when we have, for example, if we can simulate theory using Hamiltonian formalism, like people are trying to using quantum computers, then of course it's possible to calculate this direct correlation function on quark-gluon plasma or scattering amplitudes. Then of course it is possible, but currently this setup, maybe, I mean, it's not possible directly. Yeah.
But you didn't say anything about quark confinement. Is it a state in the Hamiltonian? Is it some isolated bound state or isolated point in the spectrum of the Hamiltonian? Yeah, I just wanted your opinion.
Yeah, it's a difficult question. I think it's not easy to define even an order parameter or an for confinement when you have quarks. So I think I mean the discussion really, yeah, I mean this pertains more to the chiral phase transition. All this that Jishnu has been talking about, it's more about the chiral phase transition, which is more relevant in the light quark limit. So confinement is more in the heavy quark limit. And
So
I
what
think
is your opinion?
opinion.
I'm confused. Are you answering my question or saying something else?
At the probably at the I mean at the level at which one would like, it's probably not yet answered. I mean most of us believe confinement exists, but we cannot prove it as yet. I mean it's not a it's not a proven statement as yet.
Okay.
So in my opinion is that the quarks are confined below the pseudo-critical temperature. And since this is a crossover, so this width can be very large. So maybe, yeah. So after the chiral transition or the pseudo-chiral transition, then maybe this become deconfined. But I don't know how to prove it also. So that's my opinion. If you
Yeah.
question it, definitely.
One last question. There was a remark about computer scattering from levels or level shifts. The only, well, I don't know what is done, but there is one source which is this Levinson's theorem. Is that what is used to extract? Because that relates the behavior of scattering to phase shifts. Okay?
Yes, that's the one. That's the one. Yeah, I didn't know the name of the theorem, but that's exactly how it is.
It is called Levinson's theorem, but I don't know how it is used here. But okay. And then there's something called Wigner time delay. These give data on some properties of scattering from phase shifts. So that may be, okay, I will look at the literature. I don't know it. Okay.
Can I make a brief comment?
Okay. Please. Yes.
Okay, regarding scattering amplitudes, the partition function for any field theoretic system at finite temperature can be related to scattering amplitudes. This is a field theory version of the work of Dash and Ma Bernstein from 1974.
What is it? I didn't follow.
Dash and Ma Bernstein showed that if I'm given the scattering matrix of a theory, I can calculate the temperature dependent part of the partition function from that information. This
So
is
that is hadron-hadron interactions, S-matrix formalism of QCD thermodynamics.
so in principle, the partition function, even though here it is calculated using Euclidean signature, can be related to real-time scattering amplitudes. But the actual calculation or the actual way of relating the two might be rather complicated.
Yeah, could be. So what you're saying, Parmeshwaran, is that in general, in principle, it should be possible to calculate these scattering amplitudes.
Yes.
That's the statement of the theorem.
Yes,
Whether
exactly.
it's possible in practice is a separate question.
That's right. Yeah.
Yeah.
So, Parameshwar, what Parameshwar is saying, suppose I'm given the vacuum expectation values at 0 temperature of quantum fields. Okay? From that, by using LSZ formulation, I can compute the scattering amplitude. By replacing the fields by in and out fields and so forth. And there is some time ordering involved. Fine.
Yeah.
But that calculation as it stands also goes for KMS states, where you have finite temperature states. Okay? Now, nothing is provided the quantum fields you are taking expectation values have appropriate asymptotic limits. So it seems to me that calculation, the relation of KMS states, the finite temperature states are KMS states. So KMS states to scattering all in real time at least can be formulated provided the asymptotic limits of the fields exist. So there is in fact a particle which is associated to quantum field. Okay?
Right.
At least formally we can write down the answer. Okay? I think you can write down the answer, but the calculation may be complicated.
Right. Exactly. That's what I'm saying.
Yeah. But you can write down the formula. It's not a big deal. Okay? But if the real question which is bothering many of us, I think our meeting also raises this, is are quarks confined? It appears that nobody knows.
Yeah, well, yeah, there doesn't exist a proof. A formal proof of confinement.
Well, the formal proof will consist on some understanding of the spectrum of the Hamiltonian. So the Hamiltonian spectrum of the Hamiltonian, that is the Euclidean time formulation has, in my opinion, at least I am prejudiced, there are many defects. Already in QED, it doesn't show the infrared problem and super selection rules and all kinds of things in QED. At least I don't know how to do it. The I problem that comes there, in which Goswami talked about in a very heavy way. I don't know how to do the expansions. This is already known from Kibel's work long ago. Okay? So in any case, I think the proposal will be that the spectrum of the Hamiltonian. So basically, there is no colored state. Let me use a technical language in the domain of the Hamiltonian. That should be the proof. That's what happens in the Schwinger model, in things of that kind. The spectrum of the Hamiltonian has no color, the original charge state, only the bound state. So that is a kind of proof one would like, I think. But I don't, that is quite a difficult proof, no?
Yes. Yes.
That is the thing which is deserving of $1 million price. Okay.
Yes. Yes. Yeah. So yeah, I mean, one believes that it exists, but one does not have a formal proof at this point.
Okay.
Any other questions?
Oh, by the way, though, this discussion of Dasson and Ma, sorry, not to you, but who said this S matrix, that's actually nowadays people use this non-interacting version of that, which is known as this hadron resonance gas. So that is basically come from this hadron interactions.
Yeah. Yeah.
Yeah,
But yes, its applicability. Applicability probably goes beyond the hadron resonance gas. You can also
Right.
use it to find scattering amplitudes.
Right. That is the so the first term is the non-interacting one. That is the hadron resonance gas, and the second part, when you have the interactions, you put this phase shifts and then do this scattering amplitudes of pion and proton and pion and all the other particles. Yes.
Yeah. Okay. Do we have any other questions?
But yeah, thank you, Bal, for all the comments and all the questions. That's really
Okay, ciao. We'll see you. Bye.
Okay. Okay. And it seems we don't have any other questions. So let's all thank Jishnu. Thank you very much, Jishnu, and thanks
Very
for
nice
agreeing to
talking.
this time as well. And see you around. See you around sometime.
yeah. See you around.
Bye. Bye.
Bye.
So I stop the recording now.
Yeah. Yeah.